Good afternoon, everyone, and welcome to the Institute of Advanced Studies. I'm Professor Jens Martin, I'm director of the IIS, and it's wonderful to see so many of you today. As always, geography seminars, I think we have the highest level of attendance, so thank you so much for joining us today. And thank you for those of you joining us online as well. As always, IIS is the place where we have the most exciting, the most interesting conversations about topics that really matter. And then Jens' presentation today will be a continuation of quite a few presentations we recently had about rivers, about climate, about flows. So really looking forward to that. A couple of housekeeping rules for those of you online. If you have any questions, please post them in the Q&A section. We are monitoring questions, and there should be time in the end to ask those. For those of you in the room, again, please ask the questions. Give us your comments after the presentation, and we will be also serving lunch. So there will be an opportunity after the presentation to talk to our fellow. The presentation will be recorded and will be issued on our YouTube channel and as a podcast, but we are not recording the Q&A part. So, feel free to discuss whatever you want to discuss. On that, I'll pass over to John to introduce our fellow today.
I have the real pleasure of introducing Jens here. It's a joint invitation between geography, myself, Ed Baines and Chris Keelock over in engineering. Now, brief rundown on Jens's past and then some uncovered secrets in the last few days of Jens's links to Loughborough, which I didn't know about when I did the invitation. Anyway, so Jens did his undergraduate in physics at Cambridge. Then he hung around there for a PhD in earth sciences, 2003-2007. There he moved to Switzerland and in 2013, then on to Potsdam, where he is now. And one of the reasons Jens is here is I really admire his ability to put elegant mathematics to geomorphological problems. And this has allowed him to bring ideas and concepts together, which, and at least as importantly, allows him to make things testable, providing falsifiable hypotheses and falsifiable predictions, which is the basis of science as we know it. Anyway, Jens's connections to Loughborough. Firstly, I found that Jens has collaborated with Ian Reid, although he's never actually met Ian. Never had met Ian until today. And the connection was John Laron, who Jens still supervises 3 PhD students with. Also, during his PhD, Jens was working with Dimitri Lag in Rennes and helped to propose and test the flume that Ed Baines did his PhD on, and Will is now doing his PhD on. He also has a connection with Steve Rice, who, alone no longer at Loughborough, has his legacy here, and that was proposing EGU sessions on something called biogeomorphology, which certainly has a legacy that runs around Loughborough until today. Now, I'm the useless one in this set of connections because I've known Jens for at least 10 years, and we haven't yet.
20.
And I have more grey.
Almost 20.
However, in that time, we haven't yet managed to do a concrete project together, which is at least one of the reasons that Jens is here now. We're trying to do this in the IIS visit. Anyway, I think Jens is fantastic. He's here now, and he's going to tell us something more about river valley evolution.
Thanks, John. It feels a bit funny to talk after that, like, especially if it's about me. But it's great to be here. I hope you enjoy the talk. I'm really open for questions and for criticism. Yeah, really give me a hard time. I enjoy that. And what I'm going to present is basically a summary of 5 papers that we've published over the last, say, 5 years or so. One is unpublished yet, that's in the end. And that is looking at the widths of fluvial valleys. And I have this nice title, When Rivers Kiss the Valley Walls. And I want to start with something completely different. So this is a paper I found that's pathways of commitment to get married. And there are apparently four different types of relationship there. These are dramatic, conflict-ridden, socially involved, and partner focused. And I thought this could be a little bit similar to valleys. And So you have an example of here, that's a river from Japan. Look at the dramatic lighting here, and sometimes it's really nice, and sometimes you have floods, and it's not that nice at all. And so that's kind of a dramatic valley. Then we have, this is from Nepal, no, from India in the Himalaya, very steep, lots of landsliding activities on the walls. You have glacial lake outburst floods and so on. So like the valley walls and the river don't really like each other, but they stick together anyway, right? So this is a conflict-ridden valley. These are very close. They're very steep. There's not that interaction. They stick together, partner focus, partner oriented. Slot gorge, basically. And then you have these socially involved, they are going everywhere, right? Anyway, so they're very different types of valleys, and there are very different types of valley floors. And sometimes you have seen that here, you have a valley which is as wide as a river, and sometimes it's a lot wider. And the question we set out to ask is, why is that? Like, and what determines that? Why do we care? The valleys are really important in a lot of things. In mountain landscapes, it's a really important landform for the history of settlement. Usually people move along the valleys. There's water there, there's fertile soil. You have transport roads, you have fish. And so it's a good place to settle flatland for agriculture, flatland for settling. This is actually a cut-off meander loop in the Chinese Les Plateau here. And you can see they've used it for farming and for settling. It's one of the very few places in the mountains where you have flat ground where you can set up like arable land. It's a really important part of orogenic landscape evolution as the sediment is stored in valleys. There's a long-term storage there. There are chemical processes going on, weathering, carbon cycling, and so on. It's an interesting fluvial landform. It affects flood dynamics, hydrology, floodplain ecology. There are hubs of speciation and biodiversity in mountains, like also species, animals, plants, they move along valleys to colonize different regions. And valleys are very important for setting up fisheries. So there's a lot of reasons. And we don't really know that much about valleys. There's vastly more literature on fluvial long profiles than there is on fluvial valleys in terms of quantitative treatments. We want to change that. So in this talk, I introduce our model of how valley width works, or why it works the way that's called the Poisson model. And I show you evidence, observations that we compare to the model. I'm not sure whether you can call that real generic tests yet, because the data sets that we have are not ideal for looking at the model. Like the model is very new, that's been published in 2 papers in 24 and 25. And we're still working on setting up the proper tests. And then I want to show you a relation to channel sinuosity, sinuosity of mountain channels. And this is work in progress that's actually unpublished, and it's a postdoc of mine working on it. Oh, okay, what determines valley widths? So the common hypothesis that you find in the literature, and that's basically conceptually, that's 100 years old or something like that, 120 years old. Mathematical treatment was the first one in the early 90s, where Hancock and Anderson, no, I can't use that. So Hancock and Anderson, yeah. And the idea is that the river migrates laterally, it hits the valley wall, then it undercuts this valley wall, and you have that illustrated on the right-hand side here. This wall becomes unstable, you have a sediment collapse. That sediment pile protects the valley, so the river needs to work to get rid of the sediment until it can attack the wall again. And this leads to there are various variants of this model available in the literature. And this leads to what we call the eternal widening model. And basically, as the valley goes wider, the fraction of time the river spans at the wall and erodes it and widens the valley gets less and less, because it needs to cross from one side to the other, and it's just meandering or like moving naturally within the valley, and it's less likely to be at the wall, cutting into the wall. but it will never go to zero. So you don't have a steady state, and the valleys will keep widening infinitely. And basically, your valley width depends on the time that has passed since the first widening or the first incision phase. Okay. And the width is then the time times the average widening. What we say is, no, there is a steady state. And we find scaling relationships in the landscape, talk about that a little bit later. And so the idea is very, very similar. We just add one element here. So the river migrates laterally with a speed, call it V. And the direction of migration changes, and this change in the migration direction is a stochastic process. So some point the river decides to move in the other direction and change its direction of migration. And these changes of direction are stochastic events which occur at a constant rate, are independent of each other, and so on. And so that we can model that as a Poisson process. Poisson process has a rate parameter that is constant over time. And then you have a time scale that scales like a switching time scale, an average switching time scale that scales with 1 over this rate parameter. And so then you can integrate over the time, you add the channel width, because that's a kind of the base condition, and you get this integral equation for the width of the valley. And really what we need to do now is we have to determine two parameters, which is a switching time scale or this characteristic time scale, and the lateral migration speed. We need equations for these two. And I will walk you through that a little bit, not in all of the details. You can read the papers for that, but we add to that tectonic forcing, hills of sediment supply, and we link it to the hydraulic boundary conditions. So here you have a nice animation of a meandering river. You see the lateral migration. When you look in the literature and you ask what determined this migration speed, it's a lot of different parameters that matter. Is the discharge, sediment supply, the channel geometry, grain size, obviously, the channel type, meandering channels behave different than braided channels, and so on. And it's a big debate. There's no consistent picture emerging from field data at the moment. So it's tricky to disentangle in nature, and we used an experimental approach. And really, here you have a movie of this experiment. The scale here is about 5 by 3 meters. It's a really, really big flume, okay? It's filled with sand. You have sediment and water supply from the top here. The water has been dyed blue so that you can pick it up very easily on the pictures. You have this overhead camera, and we used, or like Aaron Woofer, my collaborator, designed an algorithm to map where the water is for each of the images. And so we could track where the water is in these experiments. And then we mapped the lateral migration speed. And what we found is there's a very strong inverse correlation with the local bank height. So if you have the topography, you measure how high the banks are, you find this inverse correlation very closely with an exponent of -1. So it's inverse proportional. And if you correct for this observed relationship, basically, all the other correlations with other parameters disappear. So it's not dependent on water depth anymore. It's not dependent on discharge, not dependent on channel slope locally, and so on and so on. So that seems to be the main controlling parameter. And what we do, we can define a kind of lateral transport capacity. That's a total amount of sediment that the river can move in lateral motion per unit time, per unit channel length. So it has units of area per time. And that's a really important parameter, yeah, and that comes up shining through the talk there. So if you don't understand it, what this means, please raise your hand now and I explain it again. Any questions to that? No, okay, wonderful. Yeah, so that's a very clear picture from these experiments for this lateral transport capacity. And and this turns out to be roughly linear in discharge, in the experiments. We can debate that. It's not that important for what I'm going to show you, but just for you to know, it's roughly linear in discharge. So that would be the lateral migration rate. We can relate it by this and basically say that the speed is this lateral transport capacity times divided by the bank height. Yeah, and the bank height is about equal to the flow depth in a planar, in a normal plane, if there's no incision. Okay, here's the idea for the switching time scale. And this is probabilistic parameter. So we say it's more likely for the channel to switch if the sediment input from the site is bigger in relation to the accommodation space. So that's cross-sectional space. So we have on the left-hand side, like a bank collapse, and this material falls into the bank, and it's basically pushing the river to the other side, and that will increase the likelihood for the channel to switch direction at this location. Now, we know how much sediment is coming in because that's just the lateral transport capacity. If the river is always doing this lateral transport capacity, if the bank is higher, it will be slower, but the bank height is always like the amount of sediment coming in per unit time is always given by this lateral transport capacity. We know the cross-sectional area of the channel, and so we can take the ratio. What we have taken in this equation as well is the aspect ratio. We're basically saying it's easier for the channel to switch direction if you have a low flow depth, if the then for the same cross-sectional area than when you have a very deep channel. Okay, and so you get this equation, which is this rate parameter in the Poisson process is proportional to the lateral transport capacity divided by the flow depth squared. Okay. We can include uplift by saying the river is moving left and right, and when it's moving away at the river is inciding at the same rate as it's uplifting, but the floodplain is not, and so it's rising. And basically, you get a temporal evolution of the bank height. When the river is coming back to the same place, it will need to encounter a higher bank height than the flow depth. And so you can integrate over that. You get a logarithmic relationship. And you can include lateral sediment supply as a fraction by the fraction of time the river spans eroding the valley walls. And I'm not gonna explain the details here again. Look at the papers if you're interested. You get an equation that looks like that for the steady state valley width. So we have the steady state valley width here on the left. Looks very complicated. I'll show you what it does. But there is basically this logarithmic relationship in the middle. And you can rewrite this in terms of dimensionless parameters. One is a dimensionless valley width. We normalize the valley width with a maximum valley width. That's a channel belt width in an unconfined setting. Okay. And what we call the mobility uplift number, that's the ratio of the sediment that can be moved in lateral motion versus the sediment that is put into the system via uplift from below. And if you plot the model, it looks like this, very easy. So for low mobility uplift number on the left, that means high uplift rate, low lateral mobility, low lateral transport capacity. It limits to the channel width. On the right-hand side, high lateral mobility, low uplift, it limits to the flood belt width or the channel belt width in an unconfined setting. And you have got this connecting logarithmic function in between. This goes over about 2 orders of magnitude. This range of 2 orders of magnitude in the mobility uplift number is fixed in the model, so that doesn't change, and there's no parameters which within. And this is a nice test of that, so remember. Okay. Now you change the channel width, you push up the left-hand side or push it down, depending on how you change channel width. When you include lateral sediment supply, you can push down the right-hand side of that. You're basically decreasing the maximum. And that's all to know about the steady state part of the model. We can fully exploit the stochastic nature of that model by setting up like the switching rates, we look at a distribution rather than like a constant or average switching time. And this turns out to be a non-standard random walk. It's a so-called random walk with momentum. So it's more likely for the walker to continue in the direction as being walked in the last step than to change its direction. So it's not 50-50, but going in the same direction, maybe 80% or 90% or so. And because it's a random walk, random walks in 1D are very, very well understood. And there's a lot of mathematics we can exploit. So here's an example of that. We have in blue paths that are just generated randomly. There's the dashed line is one of these results. It's called the law of iterated logarithm, where you can get a limit to the covered area. We get the typical normal distribution of the locations of the river in the floodplain. So I didn't say that. We have time on the x-axis. We have the distance from the origin here on that. So it's a planar view of the pathway the river could take. And then you get this like a three-stage temporal evolution. Again, time on the x-axis and the width of the valley on the y-axis. There's an early linear approximation to that. Basically, before the channel switches direction, there's a linear increase of the valley width. Then it moves into an exponential phase, which goes towards a steady state. And in the end, you get a typical random walk drift, which scales with the square root of the time. And there's a lot more things you can do with these kind of things. Yeah, and I'll show a little bit more later on. There's this very rich model. You can link it directly to the hydraulic parameters of the channel. So there is only one calibration parameter in the entire model. Everything is very well physically defined. Yeah, and so it's a kind of stochastic upscaling of the river processes. Linear, exponential, steady state. You can see the flat line there, and you have here the black dots are the means of the stochastic generation, and the lines are the theoretical predictions, like the analytical equations for it, and then square root drift. Okay, I'm gonna move to observations now, and the first thing I want to show you is evidence that a random walk is a good idea, and it doesn't seem to be animated, but that's okay. And some typical features that are indicative of random walks, and I want to show you two of them. The first one is this square root drift phase, very typical for random walks. There are very few other processes that generate that. And the second one is a -3/2 power law scaling of the return time distribution, translated into floodplains, into rivers. That means this is equivalent to the age of sediments, right? So the sediment distribution in a floodplain will follow the same scaling if the random walk, the model is a good description. For the first one, we again use the experiments. I've showed you that before. So we have the sandbox experiments. We measure the area occupied by channel. We add that up. It's a cumulative measure. And then we stack the timelines. So we take each image as a starting point to be able to calculate averages. And I show you two experiments. Here's the first one. Black are the bin means. And the dashed line is a fitted relationship. You can see that the square root relationship is a really good description of that system. So random walk seems to work in some way. There's a second experiment, slightly different parameters, so different discharge here. And again, you can see square root relationship works really, really well. Now we're looking at the -2, it says -3/2 scaling typo there. So we have, again, the analytical relationships. And again, we can relate them actually to the hydraulics of the river. Yeah, there's not free, well, there's the return time the parameter, like the stochastic parameter, the lambda in the Poisson model is determining the placement of that. And we picked 3 field data sets which comply to the assumptions of the models, so where you don't have debris flows, for example, where the rivers don't have major tributaries in the study area, and where people have measured the age distributions. And this is what we found. So Scalak and Pisuto, Everett, and Huffman et al., they dated the sediments. You can see the 3 data sets, and you can see they fit quite well to this -3.5 scaling. Yeah, so seems to work as well. Now I'm moving to steady state relationships, and we can test that against various data sets. I show you 3 main data sets, and then I move into some special cases, but we just look at the main steady state relationship first. We start with the experiments again. Here we have the same setup. The only difference is here that in the center of this flume, there was an uplifting fault. So basically, the sand was pushed up from below. And you can see how the rivers narrowed, cut the valleys through there. What we've done here is we actually added the widths if there were several valleys which were actively flowed through by the river, and summed them up and compared that to the model. What is important here is that we don't have all of the necessary parameters to really test the model. So there is a fit component in there. So the models are fitted to the data, and we need to often define proxies for the mobility uplift number. Here's a reminder what we expect, this kind of S-shaped. And this is a data, 6 experiments, and the model fitted to it. And the parameter values make sense. So the flume is 3 meters wide, and the maximum width of the valley would be about 2.70 meters from this. Second example here are rivers from Tian Shan. This is the field equivalent of the same setup. So these rivers, they flow mainly along alluvial fans, shallow alluvial fans, and then flow into a region where you have uplifting faults, and they cut valleys here. I should have put a better field picture there, but you can see it on the dark gray photograph. It's a little bit small. And there are 2 regions here, and it messed up the format. Yeah, but never mind. The northern one and the southern one, and you can see the fit to these data. Again, the relationship works quite well. Also, the parameters are reasonable with what we see in the field. And there's a second data set, again, similar picture. The last data set is a special one, like Fiona Clubb has designed with co-authors, has designed an algorithm to automatically map valley widths in the field. They published a paper in 23 where they mapped valleys in the entire Himalaya as 1.6 million data points. And what we show you is binned averages, and we use as a proxy for the mobility uplift number, we use the ratio of drainage area to the steepness index of the river. And these are the data. So you can see the model fit, and there are some outliers in black on the top, which we included for the solid line fit. But you can see here again, the kind of general relationship is very closely traced by the model. What I want to point out here is this transition region, which is about 2.5 orders of magnitude. There's no parameter in the model that can actually change that. So this is quite a good evidence that the model captures something that happens in nature. But a reminder here, these are binned averages. So I also 1.6 million data points, 150 bins here. So there's like thousands of data points in each bin.
There's no, there's black spots and you've got some gray spots. What's the difference between the two?
The black spots we just classified as outliers. So in the largest valleys, there are processes which are other than fluvial. So glacial processes or large landslides that can affect that. And basically, we just did a cutoff above a particular valley width here for the means. Yeah. So there's no going into individual valleys and looking at that. It's a generic data approach in the things. Okay. So what I want to go in next is like the role of lateral sediment supply. The river needs to evacuate the material that is supplied from the hill slopes. And that limits the width, and you could see that in the pushing down the width on the right hand side of the plot, right? The maximum width it can go to. But it means that in steady state there's a balance between what the river can evacuate and what is supplied by the hill slopes. And we can exploit that for additional tests. So we have a balance equation here. This p-value is the fraction of the time that the river actually spends insiding the valley walls. We can quantify that. The wider the valley is, the smaller is this fraction of time. Yeah, obviously, if you have the valley walls right hugging the river, the river is always moving into the valley at every point. And that's close to 1. If it's very, very wide, the river will be somewhere in the middle most of the time, and it's not incising, not widening the valley. And so if hill slope sediment supply is known, we can directly test this equation. There is a nice field study by Zavala et al., published in 2023, Nature Geoscience, from Chile. And they used dating methods like cosmogenic nuclides to directly measure the retreat rates of the hill slopes along this river. And what we expect here, we can predict the width from the model using this data and compare it directly, not using this data, we can predict it from the model, from the geometry of the valleys, and compare it to these data, and compare the predicted with a measured valley width. And what we expect is a linear relationship. We can't constrain all those constants, so it's not a one-to-one relationship, but the relationship should be linear here. And here is the data for these 5 points, six points there, and you can see like this linear relationship works really well. Okay, you can make this more complicated. There are different types of valleys. Like the classical one is insiding, you have these V-shaped fluvial valleys. If you add lateral migration to that, you might get something like that the river incises, it moves laterally, you get these unpaired terraces. But there are these curious features which are paired terraces, and they look something like this. And what is interesting here is that these paired terraces are thought to form during cyclic climate changes. And so each of these stages should form under similar climatic conditions, right? So the big question here is, why does it narrow? Here's an example. That's Toro in Argentina, and you can see the different terrace levels on both sides. So there's a lot of, I think 7 levels of parallel terrace in this particular system. And you don't find them very often, but they are very popular with paleoclimate people and with paleo-fluvial landscapes, because you can date the terraces and you can construct a climatic history of that. So this gives us a sequence of comparable valleys, valleys that formed under the same climate conditions. So the river conditions should be very similar. The discharge, salmon supply, and so on, they should be comparable. But we get different valley widths. And in the model, the parameter that is independent of the valley is the lateral hill slope sediment supply. So we can test the model, ask the question, why does it narrow? And the hypothesis from previous literature here is that each climate cycle provides the same time for the widening. And so the speed should be related to the terrace height. If you remember the experiments, similar idea than what we found with the bank height. If the river cuts into higher terraces, it needs to evacuate more sediment and it will progress slower, and so it slows down. And if that is true, you should find a relationship between the width and the height of the adjacent terrace here. A negative relationship. When we look at that, these are 14 cases for alluvial rivers from a global compilation. You find a lot of different relationships. Most of them are positive and not negative. So you can falsify that model. You can dig a little bit more into the mathematics and you get actually a square root relationship, a negative one rather than a linear relationship. And again, you get this mess. It doesn't work. Yeah, you can falsify that model as well. And what does our model say? What we instead find is we have a strong relationship with the total valley width. So if we plot the depth to the top of the valley and not just the adjacent terraces against the valley width, we have this very clean inverse linear relationship. If we normalize the relationship, you can see they all fall on the same line. And the R-squareds are very good for that. So the idea is here that the lateral hill slope supply scales with the depth of the valley. You can think about back weathering of these valley walls, right? That's driven by climate in some sense. So the walls are weathering back, and that's independent of the river. So that happens on all of the terrace levels. If the sediment is routed into the river, you have sediment supply that scales with the depth of the valley rather than with the depth of the adjacent terrace. And so we have this balance equation. We can relate that to the height of the valley, and what we get is this inverse linear relationship that we actually see in the data. So paired terraces arise because valleys deepen in each climate cycle, and there is a river-independent process, back weathering of the valley wall, that supplies sediment, and you need special conditions. The sediment supply from these back weathering valley walls needs to be in such a way that it's along the river rather than focused in tributaries. So if you have a well-developed drainage system along the terraces, on the terraces, you won't get terrace sequence. That's a consequence of this interpretation of the data. Okay, final bit is on scaling relationships, or what has been observed in nature very often is that valley width scales with drainage area. Here's an example from the Clearwater River, scaling exponent of about 1. And this has been observed in many valleys. In the literature, we found about 60, 70 different cases where that scaling exponent has been measured. And they vary a lot between about 0.2 and 1.2. If we are just looking at the end members of the channel belt width and the valley width, the channel width, we should expect similar scaling exponents as you would see for classic hydraulic geometry, how the depth of the flow and the width of the flow scale with drainage area. And we've compared that. So here is a distribution that we found for all the valleys. And you can see the typical ranges for river. There are 2 different compilations for hydraulic geometry there. And they basically match. They overlap very strongly. So that's not bad, not falsified the model yet, but we can do a little bit better than that. So if we put in power law scalings for the channel width and the channel belt width into our model, we can predict a relationship for how valley width should vary along the stream. So here on this plot, you have the drainage area on the x-axis, you have the width on the y-axis, and the channel width is given by the red line. So that's a typical scaling relationship with an exponent of 0.5. Channel belt width is given by basically the same relationship, but it's bigger. Yeah, so that's a blue line here. And the model predicts these gray lines in the middle. And we have increasing uplift rate from top to bottom. So if you have lower uplift rate, basically the river goes to the channel belt width a lot quicker than when you have high uplift rate, okay? So if you plot the ratio of valley to channel width against drainage area, you should see something like this. So you have like an end member, you have this S shape again in the curve, similar to the mobility uplift number, something like this. Here is data from the Clearwater River. And it's messy in this particular river. It's the only example I found where they actually could get the data along the river in the literature. So you can kind of guess this relationship into here. But I think it needs a bit more work of doing that. But we have clear predictions what we would expect, and we should be able to tease that out with suitable field experiments. Okay, I'm coming to the last part now. I'm gonna talk about the relation to sinuosity, channel sinuosity. And I want to stress this is mainly work of a postdoc working with me, Yuji Zhong, who put this together. He also put the slides together. So if I get lost, yeah, don't blame me. There's a long-standing debate. And I'm sure you're aware of it, particularly the older geographies. Davis in the 1890s claimed, like he came up with this concept of the geographical cycle. Who's aware of that? Who knows the geographical cycle? Yeah, everybody does. So here's a summary of that. He basically says, you have views, so like there's the river sizing, and then there's more uplift, more incision, it gets rougher, and so well, it doesn't say more uplift, but it gets rougher. And then they start planation and basically get rid of the mountains. In the end, you have basically planar feature. Then you rejuvenate this mature landscape, it gets uplifted, you have a high plateau, and the rivers start inciding again, you go back to the top. That's basically the idea of that cycle. And he claims in this, or this, how it's been interpreted in his paper, is that you have meandering in this late mature stage. Everything is plain, the rivers are in the alluvium, they're happy making their meander belts. Then they get rejuvenated, it gets uplifted, and they start incising. And because they're already sinuous, they inherit this sinuosity. So if you have incised meanders, this is an inherited feature of one of these earlier mature stages where you have like a planar landscape. This has already been attacked by his contemporaries. There's been a little bit debate in the literature. It's not quite clear what Davis actually thought. Like it's not so clear that he said that or that, but it's often been interpreted that incised meanders are not active. They're inherited and they don't meander actively. Okay. Here's an example, like that's a classic one where Davis actually worked. That's what they look like, beautiful meanders here, you know, these incised meanders. There's a history of literature on that. This debate, like occasionally papers published every 20 years or so over the past 120 years. People argue, okay, there are actively meandering incised rivers. But what I want to ask here is, can we use similar ideas to look at the meandering? Because both the valley width formation and the active meandering, the sinuosity formation, depend on the lateral motion of the river. And so there should be shared parameters that determine both of these parameters. And so if we look at them together, we might learn something. So you remember we have this mobility uplift number. It's the ratio of the lateral transport capacity basically over the uplift rate. And that should control both of the parameters. I take you to the Chinese Loess Plateau. That's quite a nice study area for that. One reason is that the lithology there is homogeneous, so you don't have to worry about like these variations. So the Chinese Loess Plateau is in the middle there. There is driven by a summer monsoon, both from westerly and the southern monsoon. And there is a strong precipitation gradient if you move from the southwest to the northeast here. And there has been rejuvenation in this landscape in the Pleistocene, so like increased uplift, and you can see that a little bit here in the KSN plots. KSN is a geometric measure that we use as a proxy for uplift in these kind of fluvial landscapes, and you can see that red in the southwest here, in the southeast, sorry. They are the incised rivers, that's higher uplift rates there, and lower uplift rates going to the northwest. So we get a gradient in the uplift rate as well. And the region features beautiful meanders. Like they are beautifully meandering rivers. Here are some examples, or one example here in the Jing River. That's a field photograph. So, model as a reminder on the right-hand side. So what happens? We start with a straight river, right? We increase the mobility uplift number, so the lateral mobility relative to the uplift rate in some way, and the river starts meandering. And with this meandering, it basically starts to push out the valley walls, okay? And increase it even more meandering, more valley walls. We know that in the model at some point, the valley width goes to a steady state. So the valley width stops increasing at some point. Yeah, so we are on the right-hand limit plateau at the channel bed width. But what happens with the sinuosity? One hypothesis might be that it stays the same. So both of them just go to a plateau. Alternatively, the river could start folding on itself. The sinuosity is increasing further while valley width stays the same. Or it might be that sinuosity is actually increasing. So let's look at that first. Here we have the valley flow width in red as a function of the proxy for the mobility uplift number. Again, that's the average ratio of the drainage area over the KSN, the river steepness, which is proxy for uplift rate. Same proxy that we used in the Himalaya before, okay? And you can see that we have the channel width limit on the left-hand side. We have this transition period there, and we have a kind of limit. It's not very well defined, but a kind of limit on the right-hand side. We plot sinuosity on top of that, and you see a kind of similar picture on the left-hand side. It's a low sinuosity, where you have small valley widths, and then you have a transition region, it's going up, but sinuosity doesn't stop going up. It keeps on going. This is even more clear if you plot valley width against sinuosity, and you can see how they co-vary on the left-hand side for low values, and how valley flow width is going to a constant valley while sinuosity is keeping to increase. So if we go back to our concept, we have the second option here. Basically, the meanders keep pushing out the valley walls, and then they start folding into themselves. Sinuosity keeps increasing while valley width stays the same. Now we change the picture and we plot the width sinuosity directly against KSN, and that's a proxy for uplift rate. So we see this declining function. That's the same what Klappedal reported for the Himalaya. So you see this very nicely declining function. So that's consistent. If we put the sinuosity on top of that, we can see sinuosity increases with the uplift rate. Particularly, like, this is not an even scale here with the different bins, so it's a little bit misleading in the way that's plotted. But you can see you have these really high sinuosities at really high KSN. When you look at that in the map, where do we have these actually this high KSN? These are very localized, and you can see on this map of KSN here, the two little boxes, and all these values above KSN of 20, they come just from these two very limited regions at the outlets of the big rivers in this particular region. And here's a field photograph of that. That's what it looks like. That's the lower one, actually. No, that's the upper one of these blocks. You can see the high sinuosity valleys, and you can see that the valleys are actually hugging the river. So it's a valley that is sinuous, and not only the river. And there's the other one, you have the same picture there. So here we can extend the model. There has been this Pleistocene rejuvenation of the landscape, increasing uplift rate. The concept here is that we move through this sinuosity folding up on itself. Then you have rejuvenation. The rivers start incising. They are pushed to incise, and they inherit this particular sinuosity and narrow the valleys with a new incision. The valleys go small. When you go in the field, yeah, that's what happens here. When you go in the field, that's actually what you can see. You have these narrow valleys with a highly sinuous river here. When you look very carefully, you can see that this nose in the middle of the meander loop is lower than the surrounding, like the high walls in the background. So there seems to have been a paleo valley with a meandering river. You rejuvenate, increase the uplift rate, the river incises and inherits this particular thing, and the format is messed up. So here we have a landscape where we have both of these pictures. We have the active meandering rivers in one part of the landscape, and then we have this Davis picture of the rejuvenated, incised meanders there. And these are active, that has to be said there. They are not dormant meanders, they are active. You can actually find like cutoffs and thing there. But I think it's a really nice field site where you can show this story that goes back to Davis and kind of highlight this debate a little bit. Meanders in the Loess Plateau can be both inherited and active. And that coming to the close. So fluvial valleys are created by lateral erosion of rivers and the evacuation of the eroded sediments. We have a model for that. Very simple analytical equation that can be used in a lot of different circumstances. There's a wealth of different predictions that you can make with this model. I've showed you only a selection of that. The steady state width is due to balance of hill slope sediment supply and lateral erosion capacity of the river. And so can do more work on that. And sinuosity shares the same control parameters in these mountain rivers with complex local history. And so when rivers kiss the valley walls,
Okay.